Section 6.2, Graphs of Exponential Functions. In this section, we're going to focus on graphing exponential functions and then how to transform exponential functions. We're going to start off by graphing f of x equals b to the x. We talked about last section how f of x equals b to the x is either an increasing or decreasing function based off the size of b. We also talked about how one side of f of x equals b to the x approaches the x-axis but does not cross it. Because the shape of f of x equals b to the x is so simple in nature, all we need is 2 points to help us graph our exponential function. The two easiest numbers to plug into our exponential functions are 0 and 1. Taking a look at f of x equals 2 to the x, to graph, first we'll plug in x equals 0, meaning we're trying to evaluate f of 0, which would equal 2 to the 0, and 2 to the 0 is 1. We'll also evaluate f of 1, which is 2 to the first, which is 2. Since f of 0 equals 1, that means the point 0, 1 is on the graph of my function. And since f of 1 equals 2, then the point 1, 2 is on the graph of the function. Now we'll plot both points. There's 0, 1, there's 1, 2. Now we have to determine which side is going to rise to infinity and which side is going to get closer and closer to the x-axis. If we were to trace the graph from left to right, connecting our 2 points, we can see that we would be rising. So our right-hand side should be approaching infinity, which means the left part of our graph should be getting closer and closer to 0, which means the left-hand side should be getting closer and closer to the x-axis. But remember, our graph does not cross the x-axis. And there's our graph of f of x. Since our base is 2, which is bigger than 1, then our graph should be an increasing function. And here we can see that our graph is an increasing function. If we take a look at g of x, which equals 1/2 to the x, using the same strategy, we'll evaluate g of 0 and g of 1. G of 0 would be 1/2 to the 0th power, which is 1. G of 1 would be 1/2 to the first, which is 1/2. G of 0 equals 1 tells us 0, 1 is a point on our graph, while g of 1 equals 1/2 tells us the point 1, 1/2 is on our graph. Now we'll plot the 2 points. Now, if we were to connect our dots from right to left, we can see that we are getting closer and closer to the x-axis. So this time the right-hand side is getting closer and closer to the x-axis, while the left-hand side would have to rise to infinity. And there's our graph of g of x. Now this graph does make sense for g of x. Since our base is 1/2, which is between 0 and 1, our function is decreasing. I also noticed something quite interesting about the graphs of f and g. They both look like mirror images of each other, where the mirror is our y-axis. Do you think this is a coincidence? It's not a coincidence that the graph of f of x and g of x from the last example were mirror images of each other. Thanks to our exponent properties, 1/2 to the x is equal to 2 to the negative x. Since f of x is 2 to the x, then we have that g of x is equal to f of negative x. So if we think back to the transformations from Unit 3, the f of negative x tells us that the graph of g of x is a reflection of f of x over the y-axis. The transformations we learned back in Unit 3 can be applied to exponential functions, just like they could have been applied to any other function, whether it's x squared, x cubed, or so on and so forth. The big difference between applying the transformations to an exponential function is that one part of an exponential function that has a huge impact on its shape is the fact that one side of the graph of f of x equals b to the x approaches the x-axis, which is the line y equals 0. Because the line y equals 0 helps with the shape of the graph, when we transform the points, we also want to move the line y equals 0 as if it was a point. Now, the horizontal line that the exponential function or the transformation of an exponential function approaches is referred to as a horizontal asymptote. So in our basic functions f of x equals b to the x-axis or the line y equals 0 is a horizontal asymptote for the function. Horizontal asymptotes have to be moved when we're applying the transformations. That way we maintain the proper shape. Next, we're going to graph f of x equals -2 x to the -2 plus 3. Since we see 2 as the base of the exponential expression inside of our function, that tells me we're going to start with the graph of y equals 2 to the x, which we graphed earlier in a previous example. Now, the 2 points we're going to keep track of are the points 0, 1 and 1, 2, which were the points that I used earlier in example 1 to help us graph f of x equals 2 to the x. I also want to put something to represent the horizontal asymptote. We're going to use a dashed line to represent the horizontal asymptote. The horizontal asymptote is the x-axis, which would be the line y equals 0. Now let's go through and identify our transformations and apply them one at a time. The way we're going to determine whether a transformation is horizontal or vertical is based off of whether it's affecting the exponent or not. If we look here at this -2, notice that it's being subtracted directly from x inside of the exponent. This is an indication of a horizontal transformation. Meanwhile, if you look at the negative and the plus 3 that are not affecting the exponent, those would be indicators of a vertical transformation. So I like to do the horizontal transformations first. The x minus 2 tells us we're going to shift right 2. So each point is going to move right 2. Now for our horizontal asymptote, because it's a horizontal line, moving a horizontal line left or right is not going to change where the horizontal line is because it's moving left and right forever as it is. So our horizontal line will stay put, and we'll connect the dots to maintain the shape. Our points 0, 1, and 1, 2 would become 2, 1, and 3, 2, while our horizontal asymptote remains in place. Next, because we've handled all of our horizontal transformations, we'll now start looking at the vertical transformations. Now here we see 2 vertical transformations. We have the negative in front of the 2, and we have the plus 3. The negative tells us we do a reflection over the x-axis, while the plus 3 tells us we would shift up 3. But which should we do first? But remember, outside of the function, in this case the 2 to the x, we follow order of operations. So first, we handle the reflection over the x-axis. So if we reflect both of our points over the x-axis, the point 2, 1 moves to 2, -1, while the point 3, 2 goes to 3, negative 2. And what about the horizontal asymptote? Well, our horizontal asymptote is already the x-axis. Since we're reflecting over the x-axis, our horizontal asymptote stays in place. This time when we connect the dots for the graph, because we reflected over the x-axis, since the right was rising, the reflection, the right will be falling. Now the left will still be approaching the asymptote. Now all that's left to do is our vertical shift. So our point 2, negative 1 goes to the point 2, 2. Our point 3, negative 2 goes to the point 3, 1. Since our points are shifting up, our horizontal asymptote must also shift up. Since it started at y equals 0, the horizontal asymptote will shift to y equals 3. Now as we're connecting the dots, since the graph we shifted was falling on the right, our graph will still fall on the right, and it'll still approach the horizontal asymptote on the left. So in orange, that would be our graph of f of x, which was negative 2 raised to the x minus 2 power plus 3. To help visualize what we started with and what we ended, I erased the blue and the green graphs that we used to transform. Now you can see our end result when compared to our starting graph a little bit more clearer. Next, we're going to graph g of x equals 3 times 2 to the x plus 1 minus 1. Just like in the last problem, notice that the base of the exponential expression is 2. So just like in the last problem, we're going to start off with the graph of y equals 2 to the x, and we're going to keep track of the points 0, 1, 1, 2, and our horizontal asymptote. So let's go ahead and graph. We'll put a dotted line for the horizontal asymptote, and we've already seen the graph for y equals 2 to the x in the past two problems, and there's our graph. Now, it doesn't matter which you choose to start off with first, whether it's horizontal transformations or vertical transformations. I do like to do the horizontal transformations first. Remember, horizontal transformations are indicated inside of the exponent. So we're going to look at the 2 times x plus 1. The 2 tells us we have a horizontal compression, while the 1 tells us we have a horizontal shift. Which one of these should we do first? Well, recall that horizontal transformations behave opposite of the order of operations. While order of operations tells us we multiply first, then add, reverse that, we're going to handle the addition, then the multiplication. In other words, we're going to do the shift before the compression. So first, handling the plus 1 in the exponent, the plus 1 tells us we're shifting left 1 unit. So our point 0, 1 goes to negative 1, 1, while our point 1, 2 goes to 0, 2. As for the horizontal asymptote, because this is a horizontal transformation, and our horizontal asymptote is already a horizontal line that stretches left and right forever, our horizontal asymptote will stay in place. Now connect the dots in our graph, and there's our graph. Next, we'll do the horizontal compression. Now, since horizontal compressions involve us dividing by whatever we're multiplying to x, we'll be doing a horizontal compression by a factor of 1/2, meaning we're going to multiply all of our x values of our points by 1/2, or divide them by 2. So we have the points negative 1/2, 1, and 0, 2. The 0, 2 not moving anywhere because the x component is 0. So plotting our points, or horizontal asymptote will also not move anywhere. One thing to note, horizontal asymptotes are never affected by horizontal transformations. Because they're already horizontal lines, moving them left or right, or compressing them and stretching them horizontally is just going to maintain the same horizontal line. Now we'll connect the dots, and in purple, there's the graph of our horizontal compression that's applied to our blue graph. Now that we've finished all of our horizontal transformations, let's move to the vertical transformations. I see 2 vertical transformations, a stretch vertically by a factor of 3, or a shift down 1 unit. But remember, outside of the function, doing the vertical transformations, we follow the order of operations. So we have to do the multiplication first, meaning we have to do the stretch first. So we have our vertical stretch by a factor of 3, which means we're multiplying 3 to all of our y components. Negative 1/2, 1 from the previous graph becomes negative 1/2, 3 for this graph, while the point 0, 2 becomes the point 0, 6. As for our horizontal asymptote, since we're multiplying all of our y values by 3, 0 times 3 is 0, so our horizontal asymptote still stays at y equals 0. Plot our points, and then connect the dots. And there's the graph after our vertical stretch. Last but not least, we do have to handle the minus 1, which tells us we're going to shift down 1. So the point negative 1/2, 3 goes to negative 1/2, 2, 0, 6 goes to 0, 5. Now our horizontal asymptote does also shift down 1, and I'll shift to y equals negative 1. And in orange, there's the graph of our exponential function. I erased the graphs that we made for steps 1, 2, and 3, so that way we can better see the graph we started with in red, and the graph that we're going to end with in orange, which would be the graph of g of x, which equals 3 times 2 raised to the 2x plus 1 minus 1.